Part 5, Diffraction and Interference. In 1801, Thomas Young discovered that when monochromatic light, so light of one color, passed through two narrow slits, an interference pattern of bright and dark fringes or spaces was produced on the screen. The bright fringe was the end of the antinodal line, so constructive interference or two wave crests meeting, and the dark fringe was at the end of the nodal line, where destructive interference happened, when a wave crest and a trough meet and cancel each other out. Okay, so I got this nice little picture here, some monochromatic light shined on, so there's two spaces, so the two spaces are right here. Okay, and it made this kind of pattern of light and dark spots. Okay, awesome. So this is called Young's double slit diffraction grating, I guess, or Young's double slit experiment. Okay, this experiment done by Young demonstrated that light diffracts and interferes. As only waves undergo diffraction and interference, Young's experiment strongly suggested or gave great evidence that light has a wave nature. Okay, Young's experiment can also be used to determine or measure the wavelength of visible light. Okay, so very, very important experiment to prove that light is a wave. Okay, the idea is that when light passes through the tiny slits, single wave fronts emerge from the slit in a circular pattern. Okay, you can kind of see that as the light goes through here, so there's these nice straight waves. As they come through this tiny hole, they make these circular patterns. Okay, and then each one does that. Okay, and of course the light interferes. So the one light wave interferes with the other light wave. Come on, where's my eraser? There it is. Sorry, haha, funny. There we go. Okay, so what ends up happening is we get these areas of constructive interference where you get these super ultra bright lines where the waves reinforce each other and make these ultra high waves. Okay, and then here, and then the next one. Okay, on the screen will be at the there. Okay, so that's kind of the idea. We get these alternating patterns of constructive and destructive interference. Okay, so here's the two wavelength formulas. These are both on your formula sheet. So lambda equals d sine theta over n, and lambda equals dx over nl. Okay, so I'm going to tell you what the letters all mean, and then I'm going to show you on the next page. Okay, so it's a little bit of a messy picture, but we'll get through it, don't worry. Okay, so lambda, of course, is the wavelength measured in meters. D is the distance in between the two slits. So see these two holes here? So that distance, that's going to be D. Okay, theta is the angle from the central max. So we're going to call this guy, this bright spot right here, right in the center, we're going to call him the central max. Okay, and then the angle between that central max and whatever it is we're looking for, that's going to be theta. Okay, so if I'm looking for this distance here, theta would be the angle between those two lines. Okay, so yeah, clear as mud. Don't worry, we'll get there. Okay, x is the distance from the central max. So again, if I'm using this big angle between these two lines, then this would be x, the distance between those bright spots, those maximums. Okay, L is the distance between the slits in the screen. So this from here to here, okay, so from the slits to the screen, that is L. Okay, and N is the order of the bright or dark spot. There's no units on N, and I'm going to explain that here in just a minute. Okay, so here's another picture. Okay, so again, we have the two slits right there. So the distance between them is D. Okay, so we always end up with this central bright spot, always. Okay, now we have a first order bright spot and a second order bright spot and third and fourth, and as how many ever we have for as strong as the light source. Okay, and the first and second, third, fourth, whatever, they go on either side of the central max. So you have this next bright spot down, that's still a first order bright, then a second order bright, etc. Okay, x is the distance from the central maximum to the Well, first order bright. Okay, if I want the distance to the second order bright, it's still x. It's just, of course, the angle is different. Okay, L is the distance of the screen, and theta is the angle between the bright spot and the central max. So everything is measured from the center. Okay, now the hardest part of this, so I'm reading right here now, everyone. The hardest part of this is determining n, which is the placement of the spot. So whole numbers are for bright spots, and the dark spots are always halfway in between the bright spots, so they are half numbers. So remember, you can't see the dark spots, they're dark. Okay, you can only see the light spots. So if we have the central max, okay, the first order bright, n is 1. Second order bright, n is 2. Third order, n equals 3. Fourth, n equals 4. Now, the first order dark, where there's destructive interference, and I'll use blue here. So there's a spot right here where there is the complete and total destructive interference. Okay, and so that is, if you even, like, you can't see anything with your eyes, but even if you put up a light sensor, okay, it would pick up absolutely nothing right there. Okay, so that is when n is 1/2 or 0.5. So the dark spot in between the first and second is 1.5, okay, etc. So you will always notice the n for a dark spot, so I'm reading right on this line. N for a dark spot is always half behind its order number. So 0.5 is the first order dark. So n is 4.5 is actually the fifth order dark spot. Okay, hopefully the examples will kind of clear that up a little bit. Okay, and then the last thing to discuss is there are two common conventions for the slit distance d. The first, of course, is just to tell you what it is. Okay, the second is to give you the number of lines per meter. Okay, so when you're given this, we have to set up a simple ratio to solve for d. Okay, so example, find the distance between the slits if the diffraction grating is graded at 1200 lines per meter. Okay, so we want to find the distance between two lines, or simply one line space. Okay, so 1200 lines per meter means 1200 line spaces in 1 meter. Okay, we want one line space for d. So if we look at this, it's 1 times 1 divided by 1200. So really, if we have 1200 lines per meter, if we just take the reciprocal of that, that's going to give us d. So 1 times 1. Now, that only works for meters, because if it's for centimeters, then you got to change it. If you set up the ratio, you'll never get it wrong. So 1 line space times 1 meter divided by 1200 line spaces. Okay, so then our d works out to 8.333 times 10 to the negative 4 meters. Okay, so now we can put that into the formula and solve for whatever we need. Okay, so a couple of things. Finding out what n is, and then finding d if it's given to you in lines per meter. Okay, so let's look at some of these examples. All right, number 1. Calculate the angle of deviation of the second order maximum produced by directing monochromatic light, wavelength 4.30 times 10 to the negative 7 meters, through a diffraction grating ruled with 2.00 times 10 to the 5th lines per meter. All right, so let's just kind of draw what's going on here. Okay, so we've got these two slits in the light and a really bright light source. Okay, and it is going to shine light straight out. Okay, go through those diffraction gratings. It's going to make a central bright spot right there. Okay, the distance between these slits is going to be our d. And then I'll change colors here. Okay. So then the lines come up and we get another bright spot there, and then another one here and here. Okay, and then our angle that we're looking for is to the second bright spot. So that angle right here is what we're after. Okay, so that's kind of the idea. So the first thing we have to do is deal with this 2.00 times 10 to the 5th lines per meter. So we always have to change that. So 2.00 times 10 to the 5th lines. Okay, and that's in 1 meter. Now remember, 1 meter is exact in these kind of unit conversions, so that there's no sig digs on that one. And then we have really the distance for one line, or the space between one line, is how we do that. So one line, and then that is D. Okay, and of course we just cross multiply and divide, and we get D equals 5.00 times 10 to the negative 6 meters. Perfect. Okay, so that's that one. Now we go right to our formula. So there's two diffraction formulas. This is the one with the angle. So lambda equals D sine theta over n. Okay, so we want to find sine theta, so we'll rearrange for that. Oh, goodness. That line went a little bit too far. Sorry about that. There we go. That's better. Okay, so then the n comes up, the d divides down, and we get sine theta equals lambda n divided by d. Okay, so we just type that in. So sine theta equals, okay, so lambda was 4.30 times 10 to the negative 7 meters. N, in this case, because it is the second order maximum, remember the central is 0, the first bright is 1, the second bright is 2. Remember, if we had dark spots or nodes, remember those are halves. So the first dark would be 0.5. Yeah, you get it. Okay, anyways, so in this case, we're looking for the second bright, so n equals 2. Again, no sig digs on that, that's exact. Okay, and then d we figured out to be 5.00 times 10 to the negative 6 meters. Okay, and when we type that in, we get sine theta to equal 0.172. Okay, and then of course theta, we second sign that, and we get 9.90. 9.9, wow, that was 9.90 degrees. There we go. And there you have the first one. All right, number 2. Light falls on a pair of slits 1.28 times 10 to the negative 5 meters apart. The maxima are 4.11 times 10 to the negative 2 meters apart, and the screen is 1.00 meters away from, or 1.00 meters from the slits. What is the wavelength of light? All right, not a big deal. So again, if we're going to draw out what this looks like, so we've got the slits here, okay, we've got the screen over there. Okay, we're going to have the central bright right up here. Okay, there's our D is the distance between the slits. Right, so the light goes like so. Okay, now this one you'll notice, it just says the maxima are that far apart. So it really doesn't tell us what the n value would be. So we kind of have to use our brains and think a little bit. Okay, so if it's just saying the maxima, so there's a maxima, and then there's another one. And so we're looking for this distance, right here or right here. Okay, the idea of what's going on is that this is always going to be n equals 1, because we're looking for the distance, or we're given the distance between two bright spots, and it's always the same. So there we go, there's the x value, so that implies that n equals 1. Awesome. Okay, so then we want the wavelength of light here. Okay, so wavelength, and this is the one then without the angle. So lambda equals dx over nl. And because I want the wavelength, I don't even have to manipulate this formula, so that's certainly handy. So d, we have said, is 1.28 times 10 to the negative 5 meters. Okay, x is 4.11 times 10 to the negative 2 meters. Okay, Our N, we said, was 1, and our L is 1.00 meters. So when we type this all in, and I will just go ahead and do that now, 1.28 times 10 to the negative fifth times 4.11, 2, okay. And of course, dividing by 1 doesn't change anything, so, and we get an answer of 5.26 times 10 to the negative 7 meters. Voila! All right, there we have that one. Okay, so a student performing a diffraction experiment using light with a wavelength of 600 nanometers found that the distance between the first and fourth dark bands was 0.120 meters on a screen placed 1.40 meters away. What is the diffraction grading per meter? Okay, so let's read this and start labeling. Okay, so diffraction experiment wavelength of this. So this is the wavelength. Okay, found the distance between the first and fourth dark. So the first dark and the fourth dark. So the difference there is n equals 3. Now, if it was the first light, or the first maximum in the fourth dark, okay, well then that would be different. But the wording here, first dark, fourth dark, so the difference is n equals 3. Okay, and they're this far apart, so that is the x. The x is the distance between the bands. Okay, and then the screen is L. Okay, that's that. So what is the diffraction grading? So this is kind of the D, like it's the D-ish. Okay, the dish. That sounds weird. Okay, anyways, so it's the D-ish because we have to solve D first and then get the lines per meter. That's what I mean by that. Okay, so the formula, this is the one without the angle, so that's the dx over nl. Okay, and I want the d, right? So I'm going to find the d first. So if I rearrange, it's lambda nl over x. Okay, so lambda. Now, 600 nanometers, remember a nano is times 10 to the negative 9 meters. Now, that's not scientific notation, but your calculator can sort it out. There's no rule saying you have to put that into scientific notation. So 600 times 10 to the negative 9 meters. Okay, we've already said that the n is 3. Remember, no sig digs. Okay, the L is 1.40 meters from the screen. And the x, we said, is 0.120 meters. Okay, so that's great. So the D here, when you type all of that in, you get 2.10 times 10 to the negative 5 meters. Okay, awesome. Now remember, if we want, let's say, I don't know, n lines per meter or x lines, a lines, pick a letter. I guess we really shouldn't use n because we've already got an n, but don't worry about it. It's not a big deal. Okay, so n lines in 1 meter is going to be for one line. Remember, these are line spaces, really. So line space and then 2.10 times 10 to the negative 5 meters. So we cross multiply and divide. So really 1 times 1 divided by that. So really it's the reciprocal of the D. So the line meters is the reciprocal. So n lines per meter is 1 divided by 2.10 times 10 to the negative 5 meters. Okay, so the lines per meter is 4.76 times 10 to the 4th lines per meter. Okay. And again, I used n for number. It's different than the number between the first and fourth darks. It's not that. Okay, so I guess we could have used like A because we haven't used that yet. It's just a letter, guys. Please don't stress over it. Okay, so 4.76 times 10 to the 4th lines per meter. Awesome. Okay, now the very last thing. Oh, sorry. Let's before we go there, remember diffraction Young's experiment was huge in saying that light was a transverse wave, because only waves interfere like this. Okay, so huge deal in terms of explaining why light is a wave. Polarization is the other one that's really big on showing that light's a wave. Okay, so Young's double slit experiment and interference in general provided strong evidence that light does exhibit wave properties. However, evidence of interference could not distinguish whether the waves were transverse or longitudinal. Remember or recall in part 1, light and EMR in general was described by Maxwell as consisting of perpendicular electric and magnetic fields propagating through space at the speed of light. In other words, Maxwell predicted that light was a transverse wave. Is there evidence that this is indeed the case? Using a mechanical model, such as a rope, one can see that a transverse wave, remember that's these ones, okay, transverse wave can be linearly polarized when vibrations can only occur in one plane. Okay, so the vertically polarized transverse wave shown below in picture A can pass through a vertical slit. Okay, so basically if you can picture this, okay, if you shake a rope up and down, so it makes this nice little shape here, okay, and then put kind of a vertical box like with a lid with a hole in it like that, the light or the rope would still be able to go up and down through that box, okay, because it's in the same plane as the hole. Okay, however, if you turn that box 90 degrees so that the hole is going horizontally, but your waves are still going vertically, okay, obviously the box is going to stop the wave from going through. Okay, now in picture B here, if light was a longitudinal wave, okay, instead of not the sine wave, but a longitudinal wave like these guys, okay, then it wouldn't matter the orientation of the hole in the box lid, it would be able to get through. Okay, so anyways, okay, so the longitudinal waves in picture B, on the other hand, can pass through both slits unaffected because longitudinal waves are not linearly polarized. All right, well, what does all this mean? Okay, by a process similar to the mechanical model, electromagnetic waves can be blocked by two polarizing filters held at right angles to one another. Okay, so we can see here, okay, we've got these colored stripes down here, so two polarizing filters, one held vertically, the other held horizontally. So basically, one of those blackish squares has little holes in it, or little diffraction gratings, that are lined up vertically. The other one has those lines going horizontally. Okay, so that's why it's darker here, but you can still see the light underneath, or the colors underneath. Okay, because it only blocks out some of the light. Here, it blocks out some of the light. But when they're overlapping, okay, the one blocks out all the light except the vertical, and the other blocks out all the light except the horizontal, so they end up blocking each other, and you can't see underneath. Okay, so the photograph above can be explained by considering electromagnetic radiation as perpendicular magnetic and electric fields within the plane of polarization arbitrarily defined by the direction of the electric field. Okay, so basically all that's saying is that we put the electric field first and then we draw on the magnetic field. Okay, so remember that this is going along this direction, okay, and then the magnetic field goes along in and out from, okay, so remember that was part 1, okay, along the flat axis. Okay, so when light is produced by a light bulb, it isn't polarized, meaning that the plane of the electric field, okay, for each wave is random as the light propagates outwards in all directions. Okay, so watch this, or look at this. Okay, so when unpolarized light is incident or hits a polarizing filter, only one plane of the electric field is allowed to pass through, causing the plane polarized light to emerge. So look, here's a light bulb, okay, and EMR comes out of that, and the waves are going up and down in all, up, down, sideways in all the different directions. So if you put that through a vertical polarizing plate or filter, only the light rays that are going up and down can get through. So all these other diagonal and sideways ones are blocked. Okay, so only the vertical ones are going through. Okay, then if we take another filter and just place it horizontally, well, of course, a horizontal filter will block out everything but horizontally aligned light rays. So the vertical ones get blocked out. So the first one, we blocked everything but the vertical, and the second one, we blocked everything but the horizontal, but the only ones left were the vertical. Oh, well, that's crazy, because now, of course, there's no waves. Okay, so the polarizing effect supports the wave model of light, and in general, and in particular, the concept that light is a transverse wave composed of perpendicular oscillating electric and magnetic fields. So Young's double slit experiment advanced the idea that light was a transverse wave, or light was a wave, and then the polarization was just another huge thing to say that light was, or EMR was, a transverse wave. So a couple of really big things there. Okay, so I want you guys to practice this. This is the end of chapter 13. Okay, so this is section 13.5, starts on page 697, and I would like for you guys to do numbers 6 through 11. Again, you can work right out of your textbook, or you can print the textbook page from the workspace card. So either way, we are done chapter 13, so you will have a formative assessment, curriculum review, and a quiz on chapter 13 coming up in short order. So good luck on those, and I'll see you when we start chapter 14. Thanks, guys.